And let's see what we have from the last course. We just learned the householder transformation, and we mentioned that we would talk about 2 sessions this time, and then our ultimate goal is to get the eigenvalues of a matrix, and then with the QR method. And the QR method here is using the things to using the similar idea, but we are going to find out those matrix to make it to similar, make their symmetric symmetric diagonals matrix to similar to the linear diagonal matrix. And the linear diagonal matrix, and we would have the eigenvalues on the diagonals. And diagonal, and it means that we have diagonal, and we have diagonals above this diagonal, and then maybe we could call it is the super diagonal, and then if it is below it, and then we can call it this subdiagonal. And this is the tridiagonal matrix. We have three lines here with non-zeros components, and the other things, they are 0. And we want to transform it into a nearly diagonal one, but nearly it means that we still have some, but few entries. Those are not 0, but not on the diagonal. And this is the session 9.5, and I don't think we have the enough time to mention this into this class. We will finish the householder one, and the householder is going to prove that or you get some algorithm to transform the symmetric matrix to the tridiagonal matrix. And last time we just define the householder transformation, and the householder transformation is defined by one vector and a unit vector in L2 norm, and then we use this unit vector to define this matrix, the P equals to I minus 2W times W transpose, and then this is the N by N matrix, and we call this is the householder transformation. And we also claim that the householder transformation is symmetric and orthogonal, and we have already finished the symmetric proof. We just do the transpose of that householder transformation, and then prove that the transpose of the P equals to the transpose itself, equals to the P itself. And now, this class, we are going to prove that this one is orthogonal. And if we want to prove it is orthogonal, and then what should we do? And so here, this part is for the orthogonal proof. Orthogonal proof. And I'm going to write down the general idea first. So we are going to prove the P is orthogonal, and which means that we want to prove that the P times the P transpose equals to the identity matrix, and then this is the orthogonal definitions. And I am going to move this to the end, and this is our goal, and then we would use some details to prove it. And let's see. The P definition is I minus 2WW transpose. And we have the, let's see, P transpose again, because P is symmetric. So the P transpose is just the P itself. And we can have I to W transpose. And I hope I should have write down the vector form. And I'm going to expand these expressions And the first one, we have the I times I. And I got I here. And I got the next thing is the 2W transpose, and then times the I, and then it's just the identity matrix, and then times that W transpose. And I got W, and then W transpose. And next, I have this times the, let me see, I just do this, and then here I'm just multiplying this one with the first component and their first parenthesis, and I got minus 2W transpose. And here the last item I got is the negative 2W transpose minus times the minus the negative 2W transpose. So I got plus 4W and then W transpose and times the W and then times the W transpose. And this is the matrix multiplication, and matrix multiplication has its own associative laws, and which means that we can pick, we can get the parentheses in this expressions without changing the value, and which means that it equals to, I can put this together first and then do the multiplication first for these two items. And then what is this? What is this? W transpose times W. And by the definitions, we have the union right here, and then W transpose times W is just 1. So I just get the scalar 1 there. And this equals to the scalar 1. This one equals to the scalar 1. This one equals to a scalar 1, and which means that at the end, for that item, I got, oh, there's one missing, W transpose, and then minus W transpose. And at the end, I got this item is just the 4W and then W transpose. And you would immediately see some cancellation here. This one, and this one. And at the end, we got identity matrix, and which proves that the household transformation is orthogonal. Okay, so next we are going to, the idea is to transform, we want to transform the matrix to the sheet diagonal format. So let's see. If you take a look at the textbook, and then there are so many things, but I just want to mention one example to help you to understand the material well. And so for example, we have a simple example here, and this simple example, it looks like this. It's 4, 1, negative 2, 2, and then 1, 2, 0, 1, and negative 2, 3, negative 2. And what is our design format? Our design format, it looks like it should be the sheet diagonal, right? Sheet diagonal 1, and which means that actually this is something similar to what we have in the Gaussian animation. Gaussian animation, you are just getting the series of below here, the first line, and then the second time you're going to get this 0, and for the next iteration, we get this 0, get this 0, right? But now we want to have this format. We want to have the tridiagonal format, and we want to have this to be non-zero. And we also want to remove some things. They are here, and then they are here, they are here. And you will see the P transpose, the Householder transpose is nice because it's symmetric. And the householder transformation is nice because it's symmetric. So if we do some operations here with the householder transformation, and then we would change the things here below, and then we also would change the things above here as well. So the householder transformation is good. And then we are going to use the householder transformation to get the simplified version, the tridiagonal version. And so first, let's say this is the A1. The original matrix is just the A1. We give it numeration. Maybe it's just the A1 equals to A. And now what's the goal? We are going to transform these things into the A2. This is an iterations process. And here the iteration process, it gives us something looks like this. What we want is the matrix. And for the first iteration, and then we want to make the first column to be the desired format, the tridiagonal format. And then which means that we want to get this to be 0. And then we want to get this to be 0. This is so similar to what we have in the Gaussian animation, but this one, we have some difference here. We want the things below the first column, and then in the first column, but it's below the second element, and then to be 0. And we also have, we want the first row, the things in the first row, but up to the third column, up to the second column, they should be the 0. And this is the desired product we want from the first iteration. And in the first iteration, we are looking for this. Look for the P1 such that the A2 and then equals to the P1. P is the householder's transformation, and is the A times the P1. And this is the things we have on the textbooks as well. And once again, this is the householder's transformation. And we need to decide this householder transformations matrix to make it to be the A2 matrix. So you want to decide, let me just write out the definitions, the goal for the A2. And then we look for this transformation, which zeroes out the entries in the first column, and then beginning with the third row. And by symmetry, the symmetry, and then it also zeroes out the entries in the first column, first row, beginning with the third corner. And this is the words to describe the goal we want. And so let's see. If you want to design such an transformation here, and the very important things to decide is to decide the W in the householder transformation. And let's see. So the very important thing here, the householder transformation, and then it equals to the I, right? And then minus the W and then W transpose. And let's see. We want to have, and we also have the W L2 num is equals to 1 here. And if we want to do such an transpose, and then what do we have at the end? And then we have the A2, and then it equals to the P1 and then A and then P1. And then it equals to, if we expand it out, and then we get, there's a 2 here, 2 W transpose, and then A, and then I minus 2 W transpose. And let's calculate this things. What is the A2 looks like? If you want to decide, so all the things is to decide the W. And we want to decide this W, and then to get the decide the W vector, and then we finish our job for the first iteration, decide the W vector. So first, let's take a look at what we have in this calculation. And we have the first one, it should be the I. Let me see. So let me just do the multiplication from the left first. And then I got the A, and then minus 2 W transpose, and then A. And the next things I got, it should be the times the I, W to W transpose. And the next things I get, it should be, I'm going to do the multiplication here. And then the next things I got, it should be the A minus 2 W transpose A, and then minus 2A W transpose, and minus the 2 W transpose, and A and W transpose. And it doesn't look like anything we can get from this from those expressions. We just do some expansions here, but we still don't have any information here. But what is our goal for these transformations? We want, first of all, we want the A. So we want this to be 0, and then we want this to be 0. And actually, we can decide this. We can have, actually, we have an algorithm to decide such a vector. And I'm going to skip the calculation here, and then I will just give you the algorithm to calculate the W vectors. So our goal is to zero out the things, and then if you compare the design results, and then we just want this one to be 0, and then we want this one to 0, and then we look for the W. And the details calculation is on the textbooks, but I'm going to skip this one, and then I'll give you the algorithm to calculate the W. Is it okay? I skip the details because it takes so long. So the W here, we have the W vector here first. We are going to getting the, let me see. So the P2 here, we are going to calculate the compute the P2, P1, and then we are going to have, I think the page number is wrong. Let me see. Yes, it makes sense. It makes sense. I get the wrong page number, sorry. Okay, compute the P1 here, and then the P1 is just, we want to get the W. The very first things we want to do is to get the W, and there's an algorithm here to get all the W value, and the W value here, you will see this happen. And there's a general rule, but let's calculate the P1 first. So the alpha here, and then it equals to the negative sign. So this is intermediate values to calculate that numbers. And then we get a sign from the alpha, the A to 1. And then we do the summation here, and J equals to 2, and then AJ 1, and then do the square, and then 1/2. And then we are going to calculate another intermediate value, and then that's the R, and it equals to the 1/2 alpha square, and then minus the 1/2 A21, and then alpha, and then 1/2. And for each vectors, actually the very first, let me see, the very first component should be equals to 0. So here we have, for examples, here the W, right? And this is the 4x4 matrix. And what's the dimension of the W? The W vectors is just the W is a column vector, and then it should be the 4x1, right? And now what you need to decide is the W1, W2, W3, and W4. And I have to tell you, with this goal, we want to zero out this component, and then with that details analysis, we know that this one, the very first one, should be 0. And then that is how we zero out the things. And I know that there's a lot of confusion here, but it's from the detailed analysis, we skip a very big part, and then it takes like an hour to get the calculations there. But I tell you, the algorithm is that, well, if we want to get this 0 out, and then we need to put the W1 to 0. And then W2, W3, and W4 is decided by throwing a formula. So first, we have the W1, and then equals to 0. And then let's decide the W2. And then the W2 is just the A21, and then minus. So if you take a look at what we have here, this is the intermediate values we just calculate, and divided by the 2R, and then there's another intermediate. So that is the middle's value there. We just calculate alpha and R there. And what is the WJ? The WJ here and the WJ here, it equals to the AJ1, and then divided by the 2R, and for each J equals to 3, and then to the N. So now we have the N equals to 4, right? And let's calculate what we have here for the P1. For the P1, we just have, let's see, for the P1, and we just have 4x4 matrix. So the N dimension here is just 4. And let's see. What do we have here? We have the sign of the A21. And let me just erase all the highlighter here to make the things clear. So let's see. A21, what is the A21? A21 is just this one, right? And now I'm going to get the sign of this one, which means that I have negative sign and then 1, and then do the summation here. Summation j equals to 2. You could say I'm going to calculate the alpha, and then all the things is starting from the j equals to 2 here. And j equals to 2, and then to 4, and then aj1 square. And then doing the square root, and then what is the aj1? aj1 is the first column. It's the first column, and then all the things in the first column from the second component here. This one, this one, this one. So which means that I have 3 components in here, and then I'm going to calculate this. And you will see the process is repeating, looks like this in the next iterations. And I got the 1 square, and then negative 2 square, and then 2 square. And so if I calculate this number, and then I got negative 3, and this is my alpha. And next I got 1/2, and then negative 3 square, and then minus, and then 1/2, 1/2, and then what's the a21 again? A21 is just 1, so I have the times 1, and what's the alpha is negative 3, and I need to do the square root here, and what I get is just the square root of 6. Does that make sense? So this is just one calculation. We have some intermediate product here, the alpha and R, but our ultimate goal is to calculate the W1, W2, W3, W4. And what's the W2? W2, we are going to use the alpha and R value to calculate it. And the A21 is just the 1 minus the negative 3, and then divided by the 2R square root of 6, and then this one is just a square root 6 divided by 3. And next, so for here we just have 2 more components. We have the W3, we have the W4, and the W3, W4 is quite easy. And you will see we just need to do some divisions here. And the AJ1, what is the AJ1? A31 is the negative 2. And the A41, this is the A31 verse. So this one is A31, and divided by the 2R, and the 2R is just the 2 square root of 6. And I got the number, it should be negative 6 square root of 6. And what's the W4? W4 is just the A41 divided by 2R. And then the A41 here is just a 2, and then divided by the 2, and then square root of 6. And this is square root 6, and then divided by 6. And this is the W4, and which means that by so far, we already get all the values. And then we got all the values, the W, and then it equals to, because it's a column vector, it should equals to, so the W, it equals to 0, and then square root of 6 divided by 3, and then negative square root of 6 divided by 6, and then square root of 6 divided by 6. Does that make sense? So, and I'm going to use get the common factor out, and then that is the square root of 6 divided by 6, and then 0, and then this is the factor 2, and then negative 1 and 1. I just write down, get the common factor out because it's easier to get through the matrix multiplication. And then now, what is our P1 matrix? So maybe you just doubt this algorithm here, and then but actually there's some detailed process to divide how to calculate the W1, W2, W3, W4, and then this side product here. And now, if we have the W vector, and then actually we have the P1 household transformation, right? Let's calculate that household transformation. And the householder transformation here, and then it looks like this, and then it is just a P1, and it's the identity matrix, and then identity matrix is this one. Identity matrix in this example, it looks like this. And then minus the 2, and then that is the 2W, and then W transpose, right? And then so we have, because the W is defined in the square root of 6, and then 6, and then because we have the W times W transpose, we have this square, and we have the 0 to -1, 1 here, and 0 to -1, 1 here, because this is W and this is the W transpose. This makes sense. And then now the next calculation is to do you need to finish that matrix multiplication here. So in case that you don't know how to do the multiplication, I will perform the first few operations here. So 2 times the square root of 6 divided by 6 squared, and then I got 1/3. And now let's take a look at here. What do we have for the very first column? First component, A11. The A11 here, it should be the 0 first row times the first column, and I got 0 here. And then if I want to calculate the A21, it should be the first row. So this is A12. And then if I want to calculate the first row and then second column things, and then that is the first row, second column, and then that is 0 times 2, and then I got 0 here, and then first row, and then third column, and then I get first row, third column is 0. So you can see the calculations looks like this. So just do the vector multiplications to get the matrix here, and then the first rows, they are all zeros, and then for the second rows I have zeros, and then I got 4, -2, 2, and then zeros, and then -2, 1, -1, 0, 2, -1, 1. And I just give the details analysis, and then but now you will see something happening here. And what is the householders transformation here? You can see this is a very nice product. We get all the zeros in the first column under the 1, and then we got the zeros, all the zeros in the first row, and then except for the first item 1 there, and then all the things here is just -3, and then 2 derivative 3. And this is designed on purpose. We designed this P1 matrix on purpose because we want to zero out that matrix A component here, there. So if you do that multiplication, and then at the end, you will see this. So I want to get the multiplication, and actually I want to calculate the A2 here by this formula. And this is a similar transformation. The similar transformation, it should be the P1 transpose and then times A and the P1. But because the householder transformation is symmetric, so we can write a similar transformation in this way. It is just P1 times A times P1. And we have already get the P1, and then and you also get the A. And let's also copy down the A here, and then let's compare what we have from the A and then the A2, and then you would immediately see the difference here. And so here, I just show you the results, the A2 result, and then it's just a 4, and then -3, and then 0, and then 0. And this one is -3, 10/3, 1, 4/3, and then 0, 0, and then 1, 1/503, this one, and 403, and then negative 403, and then negative 1. So what do you see here? I design a W vector, and then I get a householder transformation. And then after the householder transformation, I get a new matrix. It's A2. But now, compared to this one, I zero out this one, and then zero out this one. And then there's one more thing. There's one more thing. Observe this one matrix. You'll find out that this matrix is still symmetric. And this is the good news, symmetric. And then this part is already desired. This part is already desired. Then what should we do next? We want to do one more thing to get it to be the tri-diagonal matrix. If we want to get this matrix to the tri-diagonal matrix, then we need to get this one to be 0, and then get this one to be 0, right? And you will see this is just a smaller dimensions problem. Actually, it's a smaller dimensional problem. And then we are going to apply the same process here. So you can treat it as like 3 by 3 matrix, right? And then you will apply those process again, and then the negative sign, and then A21, and then times that sigma sum J, and then AJ1, and then square, right? And then square, and then do the square root. And then you do that things for this one, and then you would get, okay, this 0 out, this is 0 out. I'm going to give you the common general algorithm for this one. The general algorithms is, so for each iterations, so let's say we already have the iterations matrix AK. So I'm going to give you the general algorithm first. So let us say we already got the AK matrix, and we want to do some zeros out there, and then how to calculate that PK, and we want to calculate that householder transformation. And then that is the PK. And then how to calculate this one, and then there's a formula here, and then that is the PK. And the PK, once again, we need to calculate the side product. The side product is alpha and R. And the alpha here, so I'm going to denote that things, the components in the AK matrix with the superscript. And so negative sign, and which means that this is the K plus 1 row, and then K column, okay? And it's from the matrix A, K, matrix AK. And this means that the K plus 1 row, and then K column component, in case that you cannot read this complicated notation, and then components entry of the AK matrix. Okay, so this is the meaning of this notation. And next, you will see the same thing here. We are doing the sigma sum, but sigma sum. So there in the P1, we start from the J equals to 2, but here this is the AK matrix, and then here we are going to start from the K plus 1. And that's the K plus 1 here, and then to the end, and then we have the AJK, and this is from the K matrix component, and then do the square and the square root. This is quite similar to what we have just now. And for the R, and then that's this another side product, and then 1/2 alpha squared, and then minus 1/2 alpha, alpha k plus 1, and then k, and then this is not alpha, this is the a component, and then 1 square root. So these are the side product, and then we are going to use the side product to define the vectors. And you will see a very nice result here, right? And then the matrix, the P1 matrix, and then we got 0 here, and then we got 0 here, right? And then this is designed on purpose, and then at the very first, we need the W1 to be 0. We need the W1 to be 0. And then you will see the same thing here in the AK iterations. We have to let the W1 and then W2, WK to be 0. So which means that, so let's see, this is our W vectors we want to calculate, and then the W vector, and we need to decide is, let's say this is the K iteration, and now I use the superscript to denote this is the K iteration, W1K and then W2K, and then let's say this is the n by n matrix, and then we have WNK, and for here, we have for the W1K, and then it equals to W2K, and then up to the WK, that is the K component. And let me write down this, WK and then K, WK plus 1K. And so up to the K component, they are all 0. They are all 0, they are all 0. And then we make it to be 0. And then the next thing is to get some formula to calculate the WK plus 1. And the WK plus 1 is also very special. And then we have a formula for it. And then WK plus 1, K, it could be calculated by the AK plus 1, K, that is the AK plus 1, K plus 1 row, and then K column component, and then minus alpha divided by the 2R. That is the side product we just calculate there. And this is the formulas. And thanks, girls. I just give the details analysis because the calculation is already very difficult. And for the things below the yellow part, and then we can have one very generous formula for it. And then it's just the WJ and then AJK and then divided by 2R. And this is for the K, that is for the K, the J equals to the K plus 1 and the M. So that is all the components below there. We have three major formula here, and then before the K plus 1 index, and then they are all 0. And then this part is just the another formula, and then below this part, and then there's another formula for that.
The index will start with K plus 2.
What?
The index for J.
Index for J.
K plus 2.
Yeah. Oh, let me see. It should be like K plus 2. Yeah. Below, it should be below there, not equals to there. Yeah. And with this definition of the WK, and then once again, we have the PK. And then it's just the identity matrix. And then this is the householder transformation. And that is what we want to learn today. And then do the transpose. And then we can calculate that householder transformation. And let's see, I'm going to use the color to distinguish different part here. And then we also have the middle part. And next part is to calculate the PK. And you also need to calculate the AK plus 1 with the householder transformation. And this is a general formula, and then we are going to perform the last iterations for that example, okay? And then before we end this class. And So we are going to compute that P2. I'm going to copy down the result here and then compute the P2 by using all the formulas we have here. And then you will immediately find out that it's just like a smaller dimensional problem. Smaller dimensional problem. You can treat it as a 3x3 things. Where is it? Okay, it's here. Let's do the calculation. This one. And we are going to compute the P2. And let's say, okay, the P2, and then we first of all, we have the W2, and then the W2, and then we already know that the first two components, and then it equals to 0 and 0, right? And the things we need to calculate is just the third component and the fourth component. And then we would get the household transformations W vector. And that's the unknown things we are going to calculate, this one and this one. And now we need to compute the side product. The side product, you will see it should be the A32 alpha and then equals to the sine and then A32, and then it's from the matrix A2. And where is the A32? I'm going to circle it. And this is the matrix, submatrix we want to simplify, right? And in the very first algorithm, in the P1 algorithm, right? And then we are going to pick this below the diagonals component. And then this is the negative sign and then things here. And then now this is the submatrix. And then below this diagonal, and this is the component. And this is how I remember this algorithm, not just remember the index here. This is the things below the diagonal, and then that is the A32. This makes sense. And then I'm going to do the summation, and then below the diagonal here. And that's the things. You can also memorize that index as well, but I'm not that kind of a person. Oh, it gets so confusing. And AJK 2, and then square, and then doing a square root. And this time I got, I'm to just get the sine, and then 1, and then sigma sum 1 square, and then 1/4 square, and then square root, and then I got -5/3. And this is just side products, and then I got the R, and then R equals to the 1/2, again, is alpha square, and then minus the 1/2, A32, and then 2. And you will see that is the component just below that diagonal, that submatrix. In the submatrix, that is the component below that diagonals, and that is the A32, and then alpha again, and then doing the square root. And I just plug in all the value here. And at the end, we get the computer, the calculator, and then to calculate this number, and I got the 2 square root of 5 divided by 3. And this is just the side products. And then once again, we have a formula for the WK plus 1 and then K. And that formula should be the W3, and then second, this is the 3 component. And then that formula, it says it should be 1 minus alpha divided by 2R. And then by using that side products we have here, and then to calculate that things. And at the end, I got this one. And what is the W4? W4 is another formula. The W4 is the AKJ. it should be the AJK and then divided by the 2R. So I have the AJK divided by the 2R, and then what's the AJK here? It's just this column here. The last one here is 4/3, and 4/3 and divided by there, and this is just 2, the K, and then J here equals to 4. A for 2 and then 2. And then it's 4/2, 4/3, and then divided by the 2R, the side product. And I got the square root of 5 and then divided by 5. And you have to continue your calculation by compute the P2 matrix, and then you have the A3 matrix by the P2, A2, and then P2. And the P2 is just the I minus 2W2 and then W2 transpose, right? And I'm going to skip the calculation here, but at the end, you would get such a matrix after the calculation, -3, 10/3. I just show you the results, final result, and then you will see the you will see how the householders transformations transform a matrix into a tridiagonal one. So at the end, you would get a very complicated numbers. And let me see in my life here, result here. The number should be 14975. Yeah. But at the end, this one is the specify and desired result, and then we get a tridiagonal one. And then this is the middle one, middle diagonal, and then this is a subdiagonal. Does that make sense? So all the things is just the algorithm, how to decide the W vector, and then to steal out the component here. But maybe in the middle, I skip some details how to get that algorithm formula, but it takes like 1 hour to get that formula. But the idea is just zero out one step and then by one step. And it's quite similar to the Gaussian animation, but this calculation here is more complicated. Any questions? It's more complicated than the Gaussian animation process, but we are just zeros out these things one by one. Okay, if you don't have any questions, then you are free to go. And then if you have questions, you can come here to ask me. Oh, good decisions.
用用 household 的方法去转换成一个 tridiagonal 的一个 matrix， 然后这个是并介绍为什么要转成这样，然后再去转成 QR。
其实没有说就转成这样再转成 QR 就是它就是相当于是你说这样子的话，它是那个简化的过程嘛。它如果算是这样子的话，这个 householder 也是其中的算法的一部分。然后通常的话，我觉得他们发现的过程是这样子的，他们先发现了 householder 可以转换成 tridiagonal， 然后 tridiagonal 是非常方便的。我们不是 QR 只是用来算那个 eigenvalue 对吧？然后但是其实是这个 tridiagonal 其实是对于其他计算都很方便，所以可能人们先开始是用这个 household 转成那个 tridiagonal， 然后但后来人家就发现我其实可以用这个 QR 的 result 来去计算这个就简化，就继续去简化 transform it to a nearly